So let's start with this data processing. This is what originally I'd called data hygiene. I'm calling it data processing here. I think data processing sort of is the more general concept. Data hygiene is part of data processing, and I'd like to be able to speak about a few other things as well. We will be skipping over some sections in here because we're already going to be talking about anomaly detection and outlier analysis, and part of data hygiene and data processing is to make sure that you don't have anomalies, or if you have anomalies, that you're able to identify them or flag them as potential anomalies. So this isn't something that we're going to be talking about too much, but we will talk about data cleaning, we will talk about data transformations, and we will talk about data quality, data validation. I will not be talking about data wrangling. It's just something that's easier to do when you do analysis, is to prepare or to process and to put your data into a specific format called the tidy data format. I'm just going to tell you that it exists, and I'm going to be showing you plenty of examples when we go through the anomaly detection examples in the next 5 sessions. You will see what we mean by the tidy data format. So let's start by talking about data cleaning. There's 2 quotes here that I think are worth mentioning. The first quote is from Orchard and Woodbury. It says, "The best way to treat missing data is not to have any missing data. The best way to clean your data is to not have to clean the data because all of your entries are already clean, hygienic. In practice, it's quite difficult to achieve that objective, but if you think about the way in which you collect data, you might have some ideas as to how you can reduce the amount of cleaning that you have to do. So this is just to reiterate the fact that data cleaning doesn't exist in a vacuum. It exists as part of a long pipeline that goes from data collection to communicating the results of data analysis, right? And it's connected to all of the other components. So you might be able to resolve your data cleaning issues at other stages in the pipeline. And this other quote by Isaac Asimov, the science fiction author, which perhaps is quite apropos when we're talking about anomaly detection and outlier analysis. The most exciting phrase to hear, the one that heralds the most discoveries, is not "Eureka, I've got it," but rather, that's funny. I wasn't expecting to see that here. This is anomalous. This is how you actually gain insights from situations that are data-based. By discovering things that do not behave the way you thought they should, and that forces you to expand your understanding of your situation. I'm going to present to you 2 major data cleaning philosophies, and what we'll do here is hopefully you'll be able to recognize the strengths and weaknesses of both of these approaches. We'll also talk a little bit about how we might handle missing observations, and while we won't increase familiarity with various anomaly detection or outlier tests, because that's already something that we have done or talked about, and we will keep on talking about down the road. 4 very important remarks when you embark on data analysis, and I'm sorry to say that I'm explicitly stating these remarks because in my experience, in my past as a data analyst, there's been instances where I did not heed these remarks and there was a fairly hefty price to pay. So now I want to make sure that nobody pays the price that I paid at the time. Before you do anything else, you need to make sure that you are not working on the original data set, in particular the original database, that you are working on a copy. And as you go through your process of analysis, as you go through your pipelines, and very often these are processes and pipelines that will be taking you 3, 4, 5 years to complete. You need to make copies along the way. When you work on your pipelines, you don't typically work on the full pipeline all at once. You work on them component by component. Sometimes you'll work on 2 components simultaneously, but you're really focusing on smaller pieces of your data analysis pipeline. Think of it a little bit like a cooking show, right? If a recipe takes 3 hours to prepare, they're not taping for 3 hours. They have previously prepared the recipe up to various states of completeness. And so when the host puts the cake in the oven and says, and now we cook for 45 minutes, well, no, they've already cooked something 45 minutes ago, or some of the team did, so that you can actually go and take out the cake as it's already ready. This is the equivalent of making copies along the way, right? That's going to simplify your job when you work on the pipeline. The other thing that I'm going to say that's super important is you need to document your cleaning steps and your procedures and your analysis steps as well along the way. Don't wait until the end. Cleaning is messy. You will not remember what you did 2 months ago. You might not even remember what you did a week ago. You might not be able to recognize that you wrote the code that is being used to clean these things up. Document your steps, because if you can't recognize these things or remember these things, somebody who's coming after you has no chance of figuring out what happened. Document your steps and document them cleanly. If you end up finding yourself cleaning too much, that you're always fixing 80% of your observations, say, then you need to stop. You need to question whether there's something wrong with the data collection procedure or some other stage that came before you start cleaning the data. If you have too many anomalies in your data set, something is problematic. Like, anomalies should be rare. Missing values should be rare. Now, rare could mean anything depending on the situation and the people working on it, but don't accept to be cleaning nothing but cleaning every step of the way without questioning whether this is an appropriate state to find yourself in. And finally, as you go through data cleaning, very often you will discover that the only available option to you here is to discard a record or discard an entire record. You should think twice before you do that. There are fields where this is an acceptable outcome. In particle physics, for instance, they run tons of experiments, they get tons of data, they will only look at some of the results. In particle physics, they're trying to prove the existence of a particle. It's enough for them to find a few tracks that show that the particle they were looking for was there. They don't need to look at every single thing. But if you're looking at finding anomalies and you discard records, it's conceivable that you've actually discarded the anomalies. If you're going to be encountering observations that are too problematic for a variety of data hygiene reasons, rather than discarding it, my suggestion is that you flag it as too messy, or it doesn't quite do what you want. And then when you run your analysis or specific analyses, you may or may choose to not include it in the analysis. But there might be other analyses where the messiness doesn't really come into play and you would want to include it. So don't discard observations. Or if you're going to discard them, really take your time to think about why you are discarding them. I've got 2 approaches to data cleaning that I would like to talk about with you. There are mainly philosophical approaches to cleaning and validation. There's something that I'm going to call the methodical approach, and there's something which is the narrative approach. In the methodical approach, you have a checklist of potential data issues, and you're going to go through the checklist on your data set, and you're going to flag, you're going to flag the observations or the entries that have the problems that you're finding on the checklist. In the narrative approach, what you're doing is you're exploring the data set, trying to understand it in the context in which it resides, and you're trying to spot unlikely and irregular patterns. Not through a checklist, through basically your intuition. You can think of the narrative approach as basically being akin to working out a crossword puzzle. You have your crossword puzzle and you're going to use a pen, not a pencil, a pen, and you are going to be willing to potentially put down answers which you are not certain are the right answers every once in a while, just to see if that can help you free up the rest of the grid. You are willing to make mistakes. You're willing to go back and say, no, this thing that I had thought was the right answer wasn't the right answer. I'm not erasing it so much because I don't have a pencil. I'm just going to write over it once I know what the right answer should have been. So that's the narrative approach. The mechanical approach, the methodical approach, is also you working on a crossword puzzle, but you're going to be working with a pencil, a dictionary, and you will never ever write down an answer. You'll never ever write down an answer unless you know for a fact that you have the right answer. The narrative approach, once the crossword puzzles are hard enough, will help you solve more puzzles. And it's certainly flashier. But you'll never be wrong if you use the second approach. You just might not be able to achieve your goal, which is to complete the crossword puzzle, assuming that this is in fact your goal. In practice, when you do data analysis, data cleaning, anomaly detection, you need to be able to do both types of data cleaning approaches. You need to be able to try to understand the data set and find values which don't match your understanding of what's happening, but you also need to be able to automate a number of steps. There's got to be things that you can do without having to do them every time because you've written the code for it. So you have to be able to use both the narrative approach and the methodical approach. Myself, I'm more of a narrative approach kind of person. I have a colleague, she comes from a computer science and cognitive science background, and she's a checklist person. She's a methodical person. The drawback with the methodical approach, at least the way that I'm understanding it, is it doesn't really allow for contextual understanding. If there's a type of oddity in the data set that you're currently looking at that has not been established as something worth looking at on the checklist, you will never be able to find it if all you do is the checklist. On the other hand, if you're looking for a story, if you're trying to get an understanding of the data set and how data might be missing, and you have a large data set and you happen not to look in the right direction, there might be some very easy, obvious things that you have missed. That's also not a good look. Observations can be missing 4 different flavors of missing observations. You might have a non-response. You were expecting that there should be an answer, a value here, and you did not have a value in your data set. If one of your features or fields or attributes is, say, the address of the president of the corporation, and you do not see an address there, something's up. There should have been an address. Why isn't there an address? So this is a non-response missing observation. So sometimes the presence of a blank value is indicative of potential anomalies. There could have been a data entry issue. It's conceivable that an observation was actually recorded on paper, say, but it was never entered in the data set. Now this is less and less of a problem, but with legacy data sets that could still happen. Sometimes they would have entered the wrong one. It would have been an invalid entry. The observation was recorded and it was entered. At some point, some people did the analysis and said, oh, this observation here is invalid. We'll talk about that later as well. We've removed it. So now it's missing. But it used to be there. It's just that there was reasons for us to believe that it should not have been there. Perhaps something along the lines of a previous question asked you how many kids you had and you said 0. and then this question asks you the age of your eldest child, and you give an answer which is, an actual number, well, one of these two cannot be right. And you might have had some indication to suggest you did have kids, indeed. And so you would have gone back and say, the person who entered 0 here, that is not a valid answer. I'm removing this. I don't know what the true answer is, but I know it can't be 0 based on a number of other things. And so now there's a missing value in my data set, but it's not missing in the same way that you did not enter a value originally. There might be instances where you're expecting a blank. Like this question is meant to be a follow-up on a previous question if you've answered yes, but you didn't answer yes, and so you never went to that question in the questionnaire. There should not be an answer for that question. If you have too many missing values of the first 3 types, well, that might actually indicate some issue with the data collection process. If you have too many missing values of the 4th type, then that might indicate that your questionnaire design is not up to snuff. Very poor. The truth is, nobody wants to spend their time dealing with missing values. So take the time to make sure you collect the data properly, or design your questionnaires properly so that you do not have to deal with these missing observations. What do we do when we're dealing with missing values? Well, there's basically 2 options. And the reason why we can't just say I'm doing nothing when I'm faced with missing observations is that most analytical methods, not all, most of them can not accommodate missing observations. Most of them require you to have what we call a rectangular data set, a complete full data set. Take something as simple as linear regression. At some point, you might remember that you find the solutions, the coefficients, by inverting some product here of the design matrix. So y would be the outcomes and x is all the measurements you have. So in order to find the coefficients of the linear surface of best fit, you need to compute this quantity. Well, if you have a missing value anywhere in your observations, in your data set, the matrix X as a whole, in particular X transpose X, will also have a hole, and when that time comes to compute the inverse, you will not be able to do that. The first reason why we think it's important to deal with missing values is so that you can actually run the algorithms that you want to use on these data sets. So what are your options? You can just remove the missing observations. Remove all the rows that have missing observations, then you'll have a matrix, for instance, that is full, complete. You can compute the inverse of X transpose X and you'll get an answer, a coefficient. You'll be happy. So it's very convenient from a mathematical perspective, from an algorithmic perspective, to remove the observations that are missing. But unless the data is missing completely randomly in the data set, that there isn't some reason why the data is missing, some reason which is actually linked with the thing you're trying to measure, then this is going to be biasing your results. There might be instances where this is acceptable, especially if you're dealing with very large data sets and there's only a minimal number of records that you would be removing from the data set. If you just discard everything that has a missing observation, then it might be worth your while to do so. It might be as well that you're in a situation where you can't really trust the process that would help you come up with a replacement value for the missing value. Something is fishy about it. Or you have to replace too many missing values in that record, in which case, sure, you might as well discard. The other option is if you're not going to discard the missing observation and you still want to use the data in a given algorithm, is you need to come up with a replacement value. We also call this an imputed value. There's a big drawback here, and it's a drawback that scares away a lot of people. When you are imputing missing values, when you're coming up with a replacement value, you now get a new data set that has a measurement in it. It's not the true measurement, it's the measurement that you thought might be a good replacement, and you never know for a fact what the true value would have been. You could have been right with the replacement value you come up with, you could have been. That bothers a lot of people. But you know, whenever you see data in a data set, you never know if this is actually a true value or not. There could be an error with the recording equipment. People could have lied. I mean, sometimes you catch lies. Sometimes you catch recording equipment issues. But when you don't catch them, you don't know if it's because they're not there or if you weren't good enough to catch them. So we already live with a fair amount of uncertainty regarding whether the values we observe or we have in our data sets are the true values or not. Having a problem because the replacement value might not be true, but not having the same problem or the same doubt about data in general, because you don't really have a way to verify if it's true or not, it's sort of not a consistent position to take. Very often the best option available to you will be to come up with a missing value, an imputation value. There's many instances where it wouldn't be acceptable, and it's not obvious what your stakeholders and your audience thinks about that. So you have to come up with some sort of strategy to deal with missing data, especially if part of what you're trying to do is to come up with anomaly detections. Now, it could be that your strategy, because you're looking for anomalies, is to say, hey, if we have observations with missing values, that's anomalous. I'm flagging this as an anomalous observation. No matter what, if you have missing values, you need to try to understand the missing mechanisms. Why is it that these values are missing? How are they missing? Because either it will help you fine-tune the collection process so that you do not have missing values, or it will help you fill in the holes. So data might be missing completely at random, MCAR, missing at random, MAR, and not missing at random. If it is missing completely at random, or potentially missing at random, only random, then you have a case for discarding the observations. If it is not missing at random, you cannot discard the observations. Missing completely at random, what we mean is that the presence or the absence of the item is completely independent of the values that you're interested in measuring, the value that's missing, say, and the other variables in your record. Imagine a setup where I'm walking home with a bunch of exam papers that I've marked, and perhaps they've been ordered alphabetically or by grades, and I trip over a sidewalk and all the papers spill out, and then there's a gust of wind and 3 papers get taken away and I never see them again. Now, this is missing completely at random. The fact that they're missing is unrelated to the value or the grade that they got or their last names. It's just gust of wind came, picked up 3 of them, and poof, they're gone. That's missing completely. Missing at random would be that the presence or the absence is not completely random. You might be able to account for the presence or absence by looking at auxiliary variables and some of the other values that you have. The typical examples, if you ask people whether they suffer from mental health issues or not, some people will say yes, some people will say no, and sometimes you won't have an answer. And what we found is that on average, men are more likely to skip that question or to not answer the question, to neither say yes nor no. So you can explain a little bit why some of these values might be missing by looking at the gender. The gender alone doesn't explain everything, but it provides you with some explanation as to why that might be the case. Now, among men, it could be that it's missing completely at random, but the fact that you're a man as opposed to a woman plays a little bit of a role to your likelihood of not answering this question. And apparently, historically, I don't know if any of this is still valid, but if you were to ask people their age, you would get the same. Women were perhaps more likely to skip over that question than men would have been. So the fact that somebody is not answering the question, or at least the value isn't there, is linked somehow to some other value. It's not a 100% correlation, but there might be a. And finally, not missing at random, the reason for the fact that you do not have a response here is directly related to the value of the item which is in there. If somebody asks me whether I've ever committed a felony, well, if I answer no, it could be that I've never committed a felony, or it could be that I'm lying. If I'm answering yes, presumably you can trust that I've committed a felony, but if I'm not answering, there's a pretty good chance that I'm not answering because I've committed a felony and I don't want to have it on record. So my lack of a value there is directly related to the answer that I would have been giving. So when that happens, you cannot discard the observations. There's tons of imputation methods. List-wise deletion is a form of imputation. You're saying, I'm removing the observations that have missing value. That's my solution. There's something called mean imputation or most frequent imputation. That's a method that is quite often used. Generally speaking, not a good imputation method. Better than nothing, but not necessarily a good approach. We have regression and correlation imputation as well, stochastic regression imputation. If you're dealing with time series data that changes over time, you might want to use something called the last observation carried forward. So in clinical trials, if somebody missed a reporting date, very often they will just use the last reported value for that missing date. The next observation carried backward might work as well. And then you can look at other things like k-nearest neighbors imputation. Let's find the other points that are close to this point, and let's see what they've answered for that question that you did not answer. The observations that are similar to you, what did they answer? I'm just going to give you a little illustration of what that looks like. Imagine here that we have a data set where these represent midterm grades on the horizontal axis and final exam grade on the vertical axis. And something's happened with my spreadsheet. I accidentally deleted all of the final exam grades for the students who had received 92% or above on the midterm. So all of the observations in this general area, I still have their midterm grade, but I've lost their final exam grade. Now in practice, if this happened, you just press Ctrl-Z, undo, and then you would recover what you deleted by accident. But let's assume that, I've lost this information forever. One approach is to say, well, you know what, I don't have a final exam grade for you. I can't use it. I can't include it in my data. So I'm going to be deleting all of these observations. They're gone. So originally I had 100 observations. Now I don't have 100 observations anymore. I've lost a fair number of observations. This might not be a bad idea if my goal is to try to come up with the pattern. If I'm trying to predict what the pattern of growth would be, removing these observations wouldn't really change that. I can probably still do a pretty good job of guessing what the pattern would be, even if I don't have these observations here. But, and this is a key point, these all represent students, and students that want a final grade for their course. And if I basically say, I'm sorry, I lost your final exam grade, you can't get a grade, they'll be, well, rightfully pissed. Depending on your task, list-wise deletion might be acceptable, it might also not be acceptable. If you decide to impute the mean, what you're saying is, I don't know what these values here truly were, but I'm going to look at the mean value for all of the final grades in my class. And perhaps the fairest thing I could do is to say, I've lost your final exam, but I'm willing to give you the mean grade for the student population as a whole, the ones that didn't lose their final grades. And if my ultimate goal is to come up with a data set that has the same mean as the original data set had, this would be a fantastic option. But given that the students for whom I'm missing the final exam grade are those who did very well in the midterm, they're unlikely to be satisfied with this solution. I'm basically bringing everybody's grades down here. The missing grades came from students who had not done so well on the midterm. They would presumably accept this solution. You could also do regression imputation. Well, the mean is not a bad idea in the sense that I'm using some of the information that I have, but I know a little bit more. There might be a pattern, a relationship between the x and the y here. Perhaps I can use that to predict what's missing. And again, if the idea is to just establish what the trend is, that there's a correlation between the midterm and the final, there is typically, then this would be an acceptable solution. And most students might not be super happy with this as a solution in the sense that, well, that's not my grade for sure. But some of the students would have gotten a better grade than they would have gotten otherwise. And some of them would have gotten a poorer grade, but not substantially poor. So this might be acceptable to some students. I suspect here that my student who got 100% on the final exam, she might not be super happy with this. She might say, hell no, you're not bringing me down to about this quantity here. I got 100%. I don't want you to give me 89%. But the number of people who would be unhappy with this is actually reduced to some extent. It really depends on what it is that you're trying to do. You might also do stochastic regression. You might say, look, I know what the pattern is, so I'm expecting there to be some sort of a trend here, but I also know that there's a fair amount of noise. So let me just recreate this pattern and add a bit of noise, and I'm going to be able to get, presumably at the end of the day, something, a cloud of points that looks the same as the original cloud of points. If your idea is to recover a data set that shares the same characteristics, probably not a bad idea. Most students would probably be okay with the fact that, yeah, their grades are fairly close to where they should be, but I mean, one student isn't going to be happy. Like the 100% student is now down to 82%. There's a fair amount of variation. Well, which one do you think is the best approach? Is it better to do listwise deletion, mean imputation, regression imputation, or stochastic regression imputation? It depends entirely on the context. A solution that works well in one case, it might be a horrible solution. So you really have to get a sense of what you need to do and achieve, and what the cost of choosing a specific imputation method would be. But the main takeaways, missing values, you can't just ignore them. You have to do something with them, whether it is deleting them or trying to replace them. If you know what the missing mechanism is, you can make better decisions as to what you should be doing with missing data. But typically, it is excessively difficult to determine what the missing mechanism is. You need to have studied the situation extensively. In the case of anomaly detection, thankfully, since you're trying to find observations that are unlike the others, having observations that are missing values makes them be unlike others. And so that could be a way out. You flag them as anomalous, you remove them, and you use the rest of the data set to try to find anomalous observations. It's at least a possibility. Your methods will work best if the values are missing completely at random or missing at random, but imputation methods will produce biased estimates. You cannot get away from that. If you use the mean imputation method, for instance, you're going to be creating spikes wherever the mean would be, because you're adding more values at that specific location. So you are artificially changing the nature of the distribution. The value of the center would not change, but the shape of it would change. And that could be problematic. If you do single imputation, which is to say you try to find the best guess once, then the imputed data is treated as though it was the actual data set. It becomes the true measurement, the one that you use. But you're not sure if you got the right answer or not, so that's not a good approach per se. One way out of this is to do what we call multiple imputation. You go through the process of imputing the missing values 100 times. You run your analyses 100 times on the new imputed data sets that you've created, and you look at the results in each of the 100 cases, and you basically draw the distribution of the results. It becomes a probabilistic method, and there you have a chance to reduce bias created by the noise, by the mistake on one imputation. If you're familiar with probabilities and statistics at all, this is a manifestation of the central limit theorem. Repeating the procedure time and time again allows you to remove issues related to noise or to accidental events. But no matter what you choose, remember this no free lunch theorem, and the no free lunch theorem is going to be our constant companion, a thorn in our side as we start talking about anomaly detection methods. Like, one of your questions might be, well, which one is the best anomaly detection method? And the answer is going to be, it depends, because of the no free lunch. That's the reason why things depend. You cannot get away